Thank you folks for joining. Rashid here. So today we will look into creating a microarchitecture for add immediate or add I instruction. So these are all the instructions that we will create microarchitecture, and the one I'm talking about is this one here. This is part of I type instructions, if you remember, right? I think these highlighted ones are the R type, and these II ones the I type. Okay, but this is our very first instruction in this series. So what is the instruction? So the assembly format is something like this, where you have a destination register, source register, and an immediate. Okay, so what you do is the content of this register is and this value, exactly that value inside the instruction, these two are added, and the output is put in this register RD. For example, x5, whatever is previously in x5, which is 0, then 0 plus 5 is the value goes into s6. Let's say x2 has 3, so you can also have a negative number there. Okay, this negative number multiply, let's say x2 had 3, 3 minus 4 minus 12, so x3 will be minus 12. So this immediate, so if you remember, this was the format of I type instructions. So this is I type immediate. So the format was that total how many bits we have? 32. Okay, all the instructions that we are looking right now for RV32I, which is the base integer, the basic RISC-V instruction form specs without any other additions is 32-bit. Within 32-bit, the first 7 bits, these are number of bits, and the individual blocks show what those number of bits contain. So first 7 bits are opcode. If you remember opcode, we can for different I type instruction, we need to differentiate between them, right? So this is what I was referring to. So that opcode, this is 7 bits. This is the decimal value for that. So these are all those different I type instructions. Okay, so in this case, the add I opcode is 19. So this will definitely be 19, right? So, and then the next 7 to 11 bits, this is our destination register. Now the register I use in this example are X's, but if you remember, how many general purpose register we have? 32. Okay, so X0 to X31. X31 will be somewhere. Where is X31? X30, sorry, 0 to 31. Where is X31? Oh, this guy over here. This is X3. Okay, that's what I was wondering. Okay, 1 second. This one is here. All right. So instead of, I could have used these values, RASP, T0 and all that, but for example, for these examples here, I'm using these X values, but of course the simulator I have, which I'm going to use soon, we can use these values, and it will know, okay, what values the X are. Okay, so right now I don't care which, and I know there are some very special like RA is X1 and all that. Right now I don't care about it. Right now I'm just putting any values here so that I can explain it to you. Understand? Okay, so this RD is destination register. So in this example is X6. So 7 to 11, how many bits? 5 bits. Okay, because there are 32 registers, so we have 5 bits for this and 5 bits for this. So the value here will need to be decoded to understand which register it is out of those 32, and the value 15 to 19 bits is the value our source register. This 12, 13, 14 for I type format, these 3 bits for func3. And for add I, this will be 0, and you remember there were some other values. There is some other value 0, this is 0 here, but then opcode is different. Okay, So if we can find this is 19 and then this is 0. If this is 19 and this is 0, this definitely means that it's ADDI instruction. And these last 12 to 31, these are 5 bits. These are sign numbers, if you remember. So it can range from the most negative number to most positive. So, it will have all the variations there. Again, if you don't remember, go back to the iType instruction that we did. We did few examples there and you will understand. Okay, so let's create a hardware for this. I already have created hardware, so let's maybe, okay, let's look into this. Yes, okay. So we start with first all these components that we have. Okay, are the very first time we start here and this value. So let's say this instruction is at address 0, all zeros. These are 32 bits address values, okay? And this is for in total we can have an excess of 4 gig memory. 32, and I'm assuming at address 00. How many zeros? 32 zeros. Or if you want to put an hexadecimal, there will be 8 zeros. At that, this instruction is stored. The next instruction is stored at what value? So the most significant will be 1, 2, 3, 4, 5, 6, 7, 8. So this is hexadecimal. The next value will be, these all will be the same and will be at 4. Okay, understand? But I'm assuming that before when SOC will start, the first step is we will have all the code inside flash and we will move it to instruction memory. So instructions are already sitting here. So at 0, 0, all zeros, this is the instruction, and that is exactly what we're going to execute. And once we executed this instruction, the PC will be incremented by 4. That's what we want to do. Okay, I will go slowly. This is first instruction, so it's okay if we take time, and it's okay if I do a few more videos. But I want to make sure that is you understand that, because once you understand this, the others are not going to be difficult. Okay, so first step, already we initialize this instruction memory from the flash. Okay, now we are ready to execute. So our PC, because we initially pressed reset, so it started at, or we started the SOC, and that PC is at what value? This value. We can initialize it with a different value too, but right now we are assuming our code start at 0, so this will have this address. So what happens as soon as this address appears, we immediately read whatever was at this, and I'm assuming it's this value here. Okay, we will create what kind of binary or hexadecimal value belongs to for this instruction, but let's look into this. Once this 32-bit come here, independent of what value is actually there, is this or something else, we need to create an architecture which is kind of works for anything, right? It reads this as a source register, it reads this 12-bit value, then add these two value and put the output in the destination. Correct? That's all we want to do. So this, as soon as the address is available, read data is available. So keep in mind that for reading, we are not depending on the clock cycle. That's what I'm assuming right now. Once any address comes in, the corresponding value, after a certain delay, of course, right? Things don't happen abruptly, but after a certain little bit time, the address there, all the transistors in action, and we will have this 32 value, which contains the hexadecimal equivalent, or so binary equivalent of this. In how many bits? 0 to 31 in 32 bits. All clear so far? These are 32 lines, so I'm not drawing 32 lines. I'm just representing it with a burst notation. So then what happens is the bit 19 to 15. So I have 32 wires coming here, and I'm taking out these 5 wires. bit 19, so start from 0 bit to 31, so bit number 19 till 15, these 5 I am really connecting to A1. So what is this? This is a register file. So register file means it's these are 32 registers, correct? And it's called when they are kind of clamped together, connected, placed together. So it's called a file, but it's not a file in the context of your Unix or Windows file. This is really registers. These are 32 registers. Each one is 32-bit long, but it's created in a little bit of a memory way, right? Because how many registers? So we will have R-type instructions where we can have at the same time we read 2 registers from that list, and we can at the same time write back into 1 register. So this register file, which is a memory, okay, storing 32 values, and each one is 32-bit long, and at any time we can put an address on A1 and read the data corresponding to that. Let's say if I put these 5 bits, this value 0 0 0 0 0, this is X0 register. 0 0 0 0 1, this is X1 register, and so on, right? So whatever this value for X5 will be 4 2 1. So when this value come, okay, 1 2 4, this is 7, but 5 is okay. So when this value comes, it means it's X5, correct? So that way, this value for 19 to 14, I connect to A1. As soon as I put, let's say 5, this number here, the value of register X5, it will be available on this line, which is again 32-bit. All the data in this is 32-bit, except, okay, we are branching here. That is clear? This is source 1 register. This doesn't have source 2 register because it's I-type. It only has a source and a destination register. So this one we are not connecting right now. Then from the same 32-bit instruction, 11 to 7-bit, so bit number 11 or 7 we're kind of taking out, and this will be what? The destination. Destination means we are writing back. So write line is this 3. So we put address 3, and we're going to put what we write. What we write is basically when we add this and this. So for that, what we write, we will look into it. We need to pull the content, the immediate and the source register. We need to add them and then write them. But whatever the value will come here, and the address for the, or register, whatever value will come here from a bit 11 to 7, which is 5 bits and connected here. Understand that? Good? So far, so good? You can stop the video and go back. Okay, so now in register file, we have this source register. That the one we want to read, the address here, its value is available here. Okay, fantastic. So this value is 32-bit. Our ALU, E has 2 inputs. It has 3 inputs. This one is deciding what this ALU going to do. Add, subtract, compare, and NOR, and all those things that our ALU is capable of, right? And gradually we will add that functionality, but this is going to determine that. We will see if it's 2 bits or 3 bits and how many bits we have. Like if there are 8 unique operations, then we need 3 bits. If there are 4 unique operations, we need 2 bits. If there are more than 4, less than 8, how many bits we need? 3 bit, right? So that is how we're going to decide how many bits this control will have. But it's okay, we will decide later on. So one value is definitely this, RS1. What is the other value coming here? the value that we want to add this immediate, but immediate is 12-bit. This line here needs to be 32-bit. So 31 to 20 from the same 32 we pulled here, and this is 12-bit. We need to create 32-bit. So what do? You remember sign extension? So if the most significant bit here, between here and this, the most significant, if it's 0, we just duplicate 0. And if it's 1, we duplicate 1. So that if you don't do it, then the number will change. It's no longer going to stay 1. So again, if you don't remember what a sign extension is, go to the digital design section, and in there I discussed that topic during the combinational circuits series. So that comes an output. We will look into how we create all this in hardware. That will come later on. Okay, right now, microarchitecture at block level, we kind of drawing the data path. So this 12-bit comes, output is 32-bit, comes here into this. Through this, we tell ALU you need to add the two. ALU add this and push the output into this. Okay, and this output is what? We are output the sum of these two we are writing into X6. So this output value goes back into write data. And which register we want to write, the value is over here. Now, if I put this address here, if I put this data, is this register going to be updated? No. This is a register, if you remember. Again, this is why I said prereq is digital logic design series. The flip-flops, when this is a flip-flop, if you remember that, right? The output is always available. You can read it, and that's what we did. We're reading it. But for the input to go to the output, there is a clock. Can be rise edge of the clock or fall edge of the clock. So that means writing to a flip-flop means, moving the data from input to output. So this data here will actually be written on that register when the rise edge of the clock comes. Make sense? So we don't need to right now any data memory and all that. This is our data path for this instruction. Now any value of register comes here and there. This should work fine. Okay? If you look at it, how it's going to work, there are our cycle, our time starts on the rise edge of this clock. So very first time when we put a reset, all the flaps, this gets resetted to 0, 0. Okay, so this already contains 0. So this output of this flip-flop, all right, when after the rise edge, this input data, we can always put an input. I'll make a connection. So this output data on the first rise edge was available here. Now this 0, 0 comes. This first we put this value and bring the data at the output of instruction memory. That is our fetch. Once it's available there, then based on the opcode, right? Remember the opcode and func3 bins. Now you're not seeing any opcode of this instruction that I moved, but basically that opcode, these 7 bits and these 3 bits are needed to generate what? Generate when we want to, which operation we want to do within ALU, one thing. And also there is I forgot to mention that not only clock rise edge comes, but also we need to have a write enable comes. Okay, so these two values, the write enable and for here, and for the adder ALU, what we're going to do, these two are generated from a control section. So we will have, later on we will build this, we will have which color I want to do. So based on this input will go to our control block. Okay. And that control block will generate this, and will generate another signal for. Make sense? That is not a data path. And as we add more instructions, we will see this will generate more signals. But look at this. Fetch, as soon as fetch happens, this is a combinational circuit for us, right? Because I read. Decode, all this is also combinational. The moment these inputs come, it's going to generate some signals. And they will be with some delay from here to here, they will be available. And then we're reading this source register, so that is also combinational. And at the same time, our sign extension, the moment we were reading this, sign extension happens here too. Then we add the two together. And then comes this write register. And when next clock edge comes, so on this edge we came here, next clock edge comes, we are ready to move the input here to the output of this register, or we can say we are now updating the value of this register. Make sense? And in this, after the rise edge, we do fetch and we do execute sometime around here, which I'm saying, okay, after clock cycle. This is not a time diagram, okay? We're just showing different things happening. This is the more like a action. So after a certain time of rise edge clock, we did fetch and we did decoding. And with the decoding, we knew that we have to add things, we have to generate write enable for it, and that signals are available. At this rise edge, it knows that this is write, and it was already ALU knew that it need to add numbers, so we have write data available here right before this. Okay, right now we're doing functional simulation. We are not modeling any delay happening there. So as the moment this address comes, this read comes. The moment these two inputs comes, the output is available. But in actual case, that doesn't happen. And those are the timing problem that we're going to look at later on. Right now, from functionality point of view, this is a single cycle. There's no pipelining in it. Okay? All right. And we are assuming whatever frequency we pick later on, if we pick 100 megahertz, which means this time is 10 nanosecond, we are assuming that this data going through all this and be available and stable here a little bit before this in 10 nanoseconds, so that then we can say it runs at 100 megahertz, this ADDI instruction. Is that good? It was a long video though. All right, I think we stop it here. And the next video, I will implement all this that I explained here, okay, all this functionality in Python. And that will be very interesting. And then using Python, we will make all the connections like this, and then we can run it. I mean, right now I'm not doing any simulation on it, but on the Python code, at least I can give it different values here. I assume memory is loaded with different instruction, and it can run different instruction, and we will see the data, we can print data. Okay, that's a cool thing about that model for this ADDI. All right, so stay tuned. I'll be bringing that video in a couple of days. Thank you so much. See you later. Bye.